Hi, my name is Murtaza. I lead product marketing at Gretel.ai, a comprehensive synthetic data toolkit for creating safe, private, and accurate synthetic data. In this community insights video, we're going to be meeting with Reetam Ganguli, a medical candidate at Brown University and someone who leads a bioincubator who's testing synthetic data for some powerful clinical applications. So let's dive into it. First of all, I just wanted to say thank you to Reetam Ganguli for joining us here from Brown University. Reetam is a power Gretel user. He's been using Gretel for a while. All of Gretel is really excited to have him on board and using our products for synthetic data. I think all of us here at Gretel have been super kind of impressed with like the impactful work you've been doing and really kind of interested in seeing like the results and stuff like that. A lot of folks in like the healthcare space are really interested in a lot of the applications you're building. We're hoping your story will be inspiration to others to join and do similar research. I'll give a quick intro of you, Reetam, but I'd love to like have you intro yourself since you're like such a celebrated like person. But Reetam, for our viewers and listeners who will view this, Reetam is a medical candidate at Brown University. And he also leads a bioincubator that connects clinical practitioners and researchers to develop kind of novel approaches to solving really, really pressing clinical problems. But I'll also let you introduce yourself here with this first question of Reetam. Can you kind of just introduce yourself for our viewers, explain your role at Brown University, kind of let people humanize you and kind of understand where you're coming from?
Sure, yeah, I would love to. And thanks for having me. So, as Murtaza kind of said, I'm a medical school candidate at Brown University. So, I'm going to study medicine, trying to be a doctor. And in this kind of process, I am concentrating in cancer engineering, which is kind of a mix of like computational biology and CS and statistics at Brown. And I got really interested in doing kind of like medical machine learning research. So that's kind of a lot of my work with the bioincubator is a lot of our projects took a more like digital health spin as soon as the pandemic hit because in-person work wasn't that possible. And we saw that, that was a really effective medium of doing things where I guess a lot of physicians have outcomes that they would like to predict. And right now they use more basic clinical judgment and using some kind of more automated methods like machine learning and deep learning to go and kind of aid that prediction strategy and that workflow can actually help improve clinical outcomes. So that's kind of what led me to Gretel, because a lot of the work that we were doing dealt with imbalanced data. So as I'm sure a lot of users that work in the medical space know, medical data is notorious for having terrible class imbalances. And what that means is that if you're looking at a specific outcome, like transfusion or death after surgery, intuitively, the majority of your patients are going to live after surgery, or the majority of your patients are going to be like normal and not need a transfusion. So although that's great for the patients, it's not great for the data, because if only like 1% of your patients have a transfusion reaction or die or anything like that, then it becomes difficult to go and fit machine learning models on that. And if you kind of extrapolate the issue, 50 years in the future, 100 years in the future, as we can imagine a society where medicine gets more and more increasingly advanced, but as a result, we'll see like a diminishing positives issue where, our data gets more and more scarce as to the actual positives that we're trying to predict. So that's kind of what led me to Gretel, because, synthetic data, I think, has a very, very important, powerful role to play in, the near future. When I first actually started using Gretel, I didn't really have much of a technical background. My only experience was like one introductory course in CS in college. And I, barely understood how to use Python. And that is honestly a little bit of what drew me to Gretel, because I liked how easy the console was to use. It was kind of like a plug and play kind of deal that you just upload the CSV and you don't really have to know much of the code. You just enter in here my parameters and oh wow, like the model runs. So that was kind of like, that was really nice and user friendly. And the rest of kind of my ML expertise, or can't even call it expertise, but my knowledge in ML was really just self-taught, like kind of what I found online with YouTube videos, with random resources online. And as I started kind of experimenting a little bit more in like Jupyter Notebook and all that, I realized that, like maybe using the actual like not CDK, but using the actual collabs that Gretel puts together would be kind of useful. So I like that because that had a more nuanced level of fine tuning and detail that I was able to do that I wasn't really able to, do just on the console. To be honest, technical background wise, I think if you just know very basic Python, Gretel is very accessible. I was kind of surprised that, you didn't really need lots of knowledge into like deep learning or what LSTMs are or anything like that, because, all that's kind of done in the model. It's more so just how do you tune the parameters, how do you upload and kind of play with the data frame, which is just kind of basic pandas. I think mainly just how it's structured is huge too, because most medical data frames, they're coded in kind of a weird way where it's like, if you don't like, if a respondent doesn't know what the answer is, or if the doctor doesn't know or whatever, instead of leaving it a blank, sometimes it'll be like a 9 or a -99 or 99, or it'll be like weird numbers like that. So if you're not careful, then your model will have like really weird values to work with, and then that'll skew the model. A lot of the times, like sometimes the data is even unlabeled. That's really a huge pain to work with. A lot of the times it's a mix of like text variables and numerical variables. Like sometimes instead of saying like 0 and 1 for hypertension, they'll say yes or no, or they might say absolutely, or not absolutely, like it's stuff like that, or not applicable, and then you have to kind of prepare for those kind of edge use cases. So just I would say pre-processing is a huge challenge with medical data. And I guess another kind of challenge in terms of actual model development is understanding how different fields are correlated with each other. One kind of small nuance that I wasn't really aware of before too is making sure that no other variables within your data frame like are conflated or proxy variables for your outcome variable. And kind of like a personal use case for this was that when I was trying to predict maternal transfusion, there was a variable was an attending present, which is like a higher ranking doctor. And I didn't realize it at the time, but that was a perfect predictor for if you'd have a transfusion or not, because if you have a more complex delivery, then obviously you want an attending present. So if you don't realize that, then it completely messes up your model. So I guess just really being aware of like all the variables that are there, making sure it's clean, making sure they all like interact with each other in a proper way is kind of difficult. And then you'll always get kind of like certain codes, like variables that are certain like D types or certain kinds of, they're just different in different ways that ends up, either making your model crash or throwing errors, and you have to always work around that. So postpartum hemorrhage, if you kind of break the words down, is postpartum. So after, the child passes, so after birth, bleeding. So it's basically bleeding associated during the delivery period. So as if anyone is married, has a kid, or has been blood process, that it's a little bit of bleeding is very, very common during the pregnancy process. But the issue is that for some mothers, such large tears happens, or there's no regain of uterine atony, meaning that the muscles kind of don't close up exactly the way you'd want them, so they still leave like kind of holes for blood to pour through. They lose a disproportionate amount of blood, and that's actually a huge challenge. So I didn't know this before researching into it, but it's the number 1 cause of maternal mortality all around the world, including in the US, but it poses like a massive burden in developing countries. So that kind of it becomes a huge challenge to see like, how do we mitigate it, how do we treat it. And there's kind of different buckets for, do you want to treat it while it's happening, do you want to treat it before it happens, or do you want to engage in more preventative measures? And there's lots of different kinds of medical devices and drugs and technologies in each of these different kind of time periods. The time period that we kind of focus a little bit more on was predictive analytics, to see that, well, can you predict if you're likely to have a maternal transfusion outcome before the bleeding ever happens? And maternal transfusion, as the name kind of implies, is that if you bleed a lot, you get a blood transfusion. So a couple of issues arise when you don't, I guess, when you're not prepared for postpartum hemorrhage and you're not prepared to go and transfuse a mother. The first and biggest issue is actually getting the blood. So if you kind of put yourself in the eyes or the shoes of the nurse or the doctor who's going through the delivery process with the mother, and you realize that you need to, get blood for a transfusion, then you actually have to send a nurse or another doctor to go up to the blood bank. So you have to type in across the patient, see, what blood type are they? And then you have to go and get blood that matches that blood type, and you have to bring it back. And that whole process, if you're lucky, can take maybe 5 to 10 minutes. If you're in a developed area, can take 20 plus minutes if you're in a more rural area. And if you're in a developing country, some of our user interviews suggested that it would be over 2, 3, 4 hours, which is, an extraordinarily long time to wait, especially if you're bleeding out. And getting this blood at the last minute has a drawback of, it might be blood type matched, but there's other antigens or specific kind of proteins in your blood that you can also match for. So if you just get blood during the delivery period, you might not get antigen matched blood. So that might lead to like transfusion reactions and other adverse outcomes down the line. So this all kind of long-winded way of saying that it's really important to be able to tell who's likely to bleed ahead of time and go and have blood prepped. And, if you're watching this, you might think, well, why don't you just have blood prep for everybody? And, that'd be great in a utopia. But unfortunately, there's a limited supply of blood, so it's just not possible. And if you dethaw blood and you have it ready and you don't end up using it, then the blood goes to waste. And, that's, another person who could have benefited from it that will not be able to. So then this whole kind of area of predictive analytics comes in. And that's where we have been kind of trying to work and see that, well, at the point of care, like the mother's first or one of her initial presentations to the hospital, can we go and predict if she's likely to have a maternal transfusion based on basic clinical history and demographic variables? So ideally, the majority of these are things like, your race, your income status, your, previous pregnancy information. Did you have a cesarean in the past? Stuff like that. So it's stuff that pretty much majority stuff that the mother knows off the top of her head and can enter into the model, and or the nursing staff or the physician team can go and enter into the model, and then it makes a prediction for how likely are you, based on a tailored risk score, to have a maternal transfusion or to need a maternal transfusion at the time of delivery. So that was a kind of major use case with Gretel to see, well, as I kind of mentioned, a lot of this data has terrible class balances. In our case, our training data, even though we trained on millions of patients, like close to 7 million, only like 0.5% of our data was positive for the outcome. So as you can imagine, our initial models were effectively useless because it predicted like basically no for the majority of patients. So that might have a great accuracy rate, but that in terms of actual like clinical utility doesn't mean much if you're just saying no for everybody. So that's kind of where our use case with Gretel came in, to see that, well, can we generate some synthetic data and augment the existing data that we have to go and improve our models. Like a big issue kind of that I pointed out with postpartum hemorrhage is that like 99% of the postpartum hemorrhage burden is in locations like sub-Saharan Africa that are low resource and that don't have the clinical facility to be able to go and treat all of them. So the issue then arises that, well, there's lots of big data frames for American patients because we've been kind of good about collecting all that and making those data frames accessible through the CDC. But in terms of patients from developing settings, that doesn't really exist. So if you want to train good machine learning models, then it has to be on kind of American patient data, at least for now, in terms of what's the highest amount of data volume available. But if you want to apply it to patients that are from Cameroon or Nigeria, from these different kinds of settings, it becomes kind of challenging to do. And kind of another like kind of layer on the issue is that when we looked at a prospective cohort of patients from Cameroon that we were enrolling, like close to 20% of them had a postpartum hemorrhage, versus like less than 1% in the US. So, and obviously, as you'd expect in Cameroon, pretty much like 100% of the mothers were Black, but in the US, like obviously, like that's less than 10%. So when you're training your model on the distribution of the data, then of the underlying distribution on the American patient data, then you're going to have models that are very biased towards mothers who are not Black, very biased towards mothers who don't postpartum hemorrhage. So then when you try to apply them to mothers that are from Cameroon that have different underlying distributions and different outcomes and different demographic settings, then the model doesn't generalize very well. And that was kind of one of our hopes by using Gretel, that maybe we can kind of expand the distribution and complement the American patient distribution with synthetic data from the Cameroon patient data and see if that actually helps to improve the model accuracy. I guess one main thing is kind of working a little bit more with Gretel and kind of exploring a little bit more how synthetic data augmented ML models perform on prospective cohort sets. So, we've had some issues with kind of using Gretel and a couple like errors here and there that we're kind of working around. So we're still kind of in that troubleshooting phase and seeing like, how, what, and in that troubleshooting phase of trying to ascertain what is the, maximal benefit that synthetic data can have. But kind of the preliminary results we had with some of the synthetic data were pretty promising. So we're hoping that we can kind of expand on that. In the near term, the hope is just that, we optimize our machine learning models to really be able to perform well for prospective sets. And in terms of like really kind of long-term overall in kind of clinical and in like the scope of clinical research, I think it'd be really cool, firstly, to have synthetic data to be able to go and share sensitized data. It's kind of like something that has a lot of friction against it because a lot of people, like a lot of trials have sensitive clinical data that they can't share with a lot of people. And I think that really hampers clinical innovation and medical innovation, because if I have a, cohort of transgender patients or patients from a really specific rural region or patients that have a very rare kind of disease that not a lot of people have, then that's a data set that's worth studying and exploring because, not a lot of people have access to that. But right now in the status quo, it's under so much red tape that if I want to share it with, a goodwill ML researcher, if I want to share it with an interested student trying to do like a publication, learn more about a disease, it's really hard to do that. And you have to go through a big process to add them up to the IRB and get them ethics clearance. And those barriers for the majority of people are just, it's too much. And they say, screw it, I'll use like the open access Titanic data set instead. So it definitely is. It definitely does hamper medical innovation. I would love to see the medical community and the research community get a little bit more, I guess, get a little bit better acquainted with synthetic data so that they can have a bit more faith in it and better understand what it is and how it actually upholds privacy and confidentiality. Because right now, I think the unfortunate reality is that the vast majority of doctors were, obviously pre-med in college. So they took more like bioscience oriented courses and not computational biology or CS oriented courses for the most part, generally speaking. So as a result, they don't really understand what generative neural networks are. They don't really understand what privacy impact that they have. Some of them think that data augmentation just looks like, oh, you're just adding like like a number, you're like shifting all the variables up by +1 or something like that. So it becomes, it becomes kind of difficult to explain that. And that's a challenge, I think, organizations like Gretel and synthetic data publications in the medical literature will hope to advance in the future. But once that happens, I mean, I would love to see as like kind of a gold standard in medicine that people say, oh yeah, like I can't share my actual data with you, but here's your synthetic data with these same underlying statistical distributions and properties that you can study and have, valid results on. And here, let me share it with you. And then we can have more medical advancement, hopefully see some better cures. And secondly, I would love to see medical data, like as a standard of care, have an option for kind of synthetic data augmentation as easily as something that's kind of like in the EHR, that's in like medical research platforms, where you can kind of click a button and it's like, yeah, I'd like to balance a distribution of like death, or I'd like to balance a distribution of sepsis or whatever. And then all of a sudden, a lot of like accurate synthetic data is made to kind of balance your data and have a good train set for any kind of machine learning model that you're trying to apply prospectively. Obviously, I think both the medical space and synthetic data space have a bit of a ways to go before that becomes a reality, but I'm really hopeful that could be something in my lifetime, hopefully when I'm like a physician way down the road.
Yeah, I mean, pretty much like all of Gretel is mission oriented to solve those two problems. Like, how can we make private data, sensitive data safe to share so we could power kind of that next generation of innovation, and medical data is like a huge focus for us, and this, and also like that accuracy part, like that's so important for us, and as a company I think we talk about it all the time.
Like, so to kind of retrace my steps, essentially I was in a place where I had like 7 million patients, like 99.5% of these patients didn't have the transfusion outcome, like under 0.5% did. So then when we were training our machine learning models, it's like, great, like the accuracy is super high. But then as far as the actual AUCs go and the like positive predictive values and all that, it's really low. So then kind of the first approach that I tried is that, why don't we reduce the number of negative samples? Maybe that's kind of crowding the results. It's like, okay, sure, we can reduce it by, half. We can cut out like 5 million patients, whatever. But as we did that, like the AUCs, improved marginally, but there wasn't like a huge like tangible benefit. And then in that process, it's also like we were losing important data, and we didn't want to sacrifice those important correlations within the data just to not crowd out the positive sample. Then we tried, can we try like overpopulating the positive sample? So can we try augmenting and creating more of those records? Can we try using something like SMOTE? And I think, even when we used SMOTE, there wasn't, I think it might have even harmed our AUC. I'm kind of forgetting it. Well, either did not help or harmed. So that wasn't great, because I think SMOTE relies on a little bit more of like depends which type you use, but the most common one I think has the KNN algorithm, which depending on what the actual class balance issue that you're dealing with could actually help to further the issue as opposed to solve it. So then at that point it's a little frustrating, because it's like, well, what do we do with this data? It took us a long time to clean it, and it's an outcome we really care about. So then as we did more research into it, we kind of came to the conclusion that our best bet would be to have some kind of platform that can properly data augment, and not just like, re-replicate the existing columns that are positive, but actually capture the underlying statistical distribution, underlying PCA, underlying statistical properties, and be able to actually repopulate the data with patients that follow this kind of distribution, with the hopes that actually improves the model. And as far as we could see, that has seemed to be the best approach. If there are other approaches that we don't know about, I would obviously love to learn about them, but so far I haven't quite come across any.
And thank you for taking out the time, Reetam. We really enjoy working with you. I've been really kind of amazing to kind of hear your work and the impact that's had, and super excited to see where it goes really from here. So do stay in touch, but leaving it to you if you have any kind of parting thoughts.
No, thank you. I'm mainly just like, I just want to express my gratitude to the Gretel team. I think John especially, he's been super helpful in helping us troubleshoot the models, and I think it's just really taken aback by how, I guess, open and accessible the Gretel team has been to me. Even though I was just kind of a ML researcher, I didn't really have a stake in the company or anything. But it's a phenomenal team. I really love the work you guys are doing. So thank you for having me. It's been a pleasure.
Thank you so much for tuning in, and thank you to Reetam for joining us. If you would like to explore clinical applications, healthcare use cases, or any other applications of synthetic data, feel free to visit Gretel.ai below. If you visit that link, you create a free Gretel account and get free credits to synthesize your first data set in 60 seconds or 5 clicks. Happy synthesizing, and thanks for joining us.